I would like to spend a little bit of time reviewing your underlying momentum things that you should have learned last year, that you should still remember, and
Keyword being should, but we all forgot.
that's why we're reviewing. To see if you remember.
Can I review what you never heard?
I remember. Okay, momentum was described by Newton as a quantity of motion. So when Newton thought of motion, he thought of motion in terms of momentum. I tend to think of momentum as what you don't want to hit you in the face.
Yes.
So when something is flying toward your face outside of sharp points, what do you not want it to contain?
Like,
I said no sharp points, other than sharp points. What do you not want it to contain? Yeah, mass. Would you rather have a tennis ball or Bob flying toward your face?
What? I need
Depends.
I need a Bob, please.
tennis ball. I think tennis ball is
It's a trick question.
How much is Bob weigh?
Exactly.
And the other factor is velocity. Would you rather catch a ball thrown by a 6-year-old
Done.
or by Randy Johnson?
by Rand.
And
Sure.
Just like the I can do it.
Randy Johnson is a major league pitcher. At least was.
Was he a quarterback?
Yeah, he was a quarterback for the goal team.
And he could throw over 100 miles an hour.
Oh my god.
Arizona Diamondbacks.
I don't want to do that.
Yeah. Anyway, the point is the two factors that are involved are mass and velocity. And if you think about it, it makes sense because, again, if a tennis ball or Bob is flying toward your face at the same speed, you're going to say, I would prefer the tennis ball to hit me in the face. And if you have a ball thrown by a 6-year-old or Randy Johnson, you're going to say, I'd like the 6-year-old to throw the ball in my face. So the two factors involved are mass and velocity. The more mass you have, the more velocity you have, the more momentum you have. So our formula is nice and simple. It's just P equals mv. And that makes sense because m is mass and v is velocity. Hey, what do you know? So mass, of course, is in kilograms. Velocity, of course, is in meters per second. So that part is not anything unusual. We understand that. So the unit for P, of course, was? Well, if I multiply a kilogram times a meter per second, I'm going to get a kilogram meter per second. So the unit for momentum is going to be kilogram meter per second. Now, ideally, you look at that and you say, hey, that looks kind of like a Newton. Very good. So it should look kind of like a Newton. If you remember, a Newton was equal to a kilogram meter per second squared. So a kilogram meter per second squared is a Newton, and that looks very similar to what we have down here for momentum's unit, except I have an extra s at the bottom. So if I take that off, I can say that's 2 s's. How do I get rid of an s at the bottom? I multiply by an s at the top. So if I multiply by an s at the top, that would cancel out. But if I multiply the right side by s, I have to multiply the left side by s also. So if I want to get kilogram meter per second, that would be the same as a Newton second. So which way will you see me write it most of the time? Newton second. Why?
Right?
Because I'm lazy. That's only 2 letters, and this is 4 letters and a slash, and 2 letters is easier, so I tend to write Newton seconds more often. Hopefully that makes sense to you, right? Now, momentum is a vector term, which means
Direction.
direction is very important. So when we're talking about momentum, we have to consider what direction it's going. So if 2 things are hitting each other, depends on the way that they're going. So if we make little drawings and we put little arrows on our drawings, that helps us to keep our direction straight, and everything will make it a lot easier. So most people, the only thing that messes them up is they don't keep track of their directions well. So if we can avoid that, we have it made. How is it that we change momentum?
With
Well, again, what are the two factors in momentum?
Mass
Mass and velocity. Which one's easier to change?
velocity.
well, if you're shooting,
Yeah, clearly the velocity is going to be easier to change than the mass is. So how do I change the velocity of something?
by hitting it with a
Yeah, I shove on it. So we apply a force over some time period, and this is known as an impulse. An impulse is a force times a time, and that force times the time causes a change in momentum or a delta P. Whenever I shove on something, I'm either going to speed it up or slow it down or change its direction. Any of these would change its momentum. Now, if I shove with it, I'm going to increase its momentum. If I shove against it, I'm going to decrease its momentum. If I shove it some sideways component, then I'm going to just change the direction of the momentum, which still changes the momentum. If you're playing air hockey, you change the momentum of the puck when? When you hit it. So you provide a impulse. Okay. So, yeah. What kind of time interval is involved when you're playing air hockey? Big T or small T? Very small T, just back in. Yeah. Okay, so it doesn't have to be that fast, but it often is in a collision. So a delta anything, of course, is final minus initial, so a delta P is really P final minus P initial. And again, since the velocity part, not the mass part, changes, we could also write that as M delta V or M times Vf minus Vi. So that's the same as the delta P. So that gives us our impulse equation that looks like Ft equals M delta V equals delta P. And again, that's an odd looking equation because it has two equal signs. Now, we don't use the entire thing at any one time. We only use 2 out of the 3 parts at any given moment. So Ft equals M delta V, or Ft equals delta P, or M delta V equals delta P. Whatever way we have the stuff. So, depends on which components we have. Ft is force times time, or impulse. So this is again just saying an impulse causes a change in momentum. Does this all sound familiar?
Yeah.
And by the way, the PSAT test is going to be on the 25th. You can sign up. Sorry. That's a good thing for you to take. You can wear scholarships. Yeah. And then that's on their scholarship. And you're in Riverview. Now they have PSAT. Well, I walked into school one morning and my counselor said, "Here, I want you to take this test." And then shoved me in the room and made me take this test. And that was how much preparation I had. Things were different back then. Okay, anybody still need this? Groovy. So yeah, we talked about impulse as being important with yeah, if you're driving in your little car and this tree jumps out in front of you, then you are in for a big impulse, right?
Yes.
Okay, so if we're in for an impulse, then again, Ft is equal to m delta v. What's going to kill you?
The impulse. Because usually
The thing that could kill you is the force. If the force is sufficiently large, then your body will suffer enough damage that you die. This is bad. Now, what can we not change?
time has.
We can't change the mass. The mass you happen to have when you hit the collision is the mass that you happen to have when you hit the collision. And you're saying, well, isn't that true of the delta V also? Because, I mean, the speed you are going when you hit something is the speed you're going when you hit something. And yes and no. If it was just the V, yes. There's nothing you could do about your initial velocity because that is what it is when you hit. But the delta V, you can do something about, and that's the way that we design your car. Your car can be designed to bounce, or your car can be designed to stick with the object that it hits. And your car is designed to stick with the object that you hit. And the reason for this is, again, if I'm coming this way with 10 meters per second, and I bounce back this way at 10 meters per second, that's a delta V of 20 meters per second. And this one's going backwards, so it's negative. So if we take final minus initial, we get negative 10 minus 10 is negative 20, right? So that's a change of velocity of 20. Now, if I go along and I'm going 10 meters per second and I stop, that's a delta V of, hey, that's only 10 meters per second. So if this is twice as much when I bounce as it is when I stick, then the force is going to be twice as big. So you see why we design your cars to stick together instead of bounce? Yeah, you say, hey, that's good for me. So bumper cars are fun because you're only going like 2 miles an hour. When you're going 20 miles an hour, bumper cars aren't fun anymore. It's just damaging. So, yeah, even at 2 miles an hour, bumper cars don't have to be fun. Sometimes you walk out there and go, ow. Okay. Anyway. So there's nothing we can do with this other than that. So we design your cars to be this, so that makes this side as small as possible. But here's our other problem. And this is a very sad problem. How much time does a wreck take? Very, very, very small. So if this T is very, very, very tiny, then that means the F is very, very big. That's bad. Because again, the F is what's going to kill you.
Yeah.
So what we want to do is we want to increase at all possible our time. If we can make my time a little bit bigger, then the force gets... Okay, but the good news about the bad news is since this time is so tiny, any change we make to it is going to be a substantial change. Does this make sense?
Yeah.
So this is why we put you in this little inertial restraint. When I put you in that little inertial restraint, then what happens is your car can now slow down over a bigger time period. Because when the car comes along, again, I can build your car so it's a tank. I mean, if I build my car so it's a tank, then it's going to hit the tree and go bonk and stop. Or I can build your car to fall apart. So when it hits, it goes... Which one takes more time? Yeah. The tank goes bink, and the time interval is very tiny. The other one goes, and that takes a bigger time. If this takes a bigger time, that might increase that time by a factor of 10. So if this is 10 times bigger, then the F is 10 times smaller. And you're saying that's still a very small time period, but 10 times the tiny thing is, it didn't seem to get that much bigger, but it's 10 times longer. So that means the force on your body is 10 times slower. Now, the reason that inertial restraint is so important is that whole crunching happens in such a small time period that you're flying off the seat, and then you hit a now stationary dashboard, windshield, steering wheel, whatever happens to be in front of you at the moment. This is not good. But if you're stapled to your car with your inertial restraint, then that means as your car is slowing down over that bigger time interval, your body is slowing down over that bigger time interval. Make sense? Yes. That's also the concept behind an airbag. If we hook up an airbag in there and it's up there, then you're smooshing the airbag over again a substantially longer time period, which means the force on your body is less. Yeah. So seatbelts are very, 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 very good ideas. When I was a kid, they were just inventing seatbelts. It came out in the early 60s. Before that, you got into wreck, and people would die in these wrecks that were 25 miles an hour. Because a 25-mile-an-hour wreck, you die. You don't think, wow, that's so slow. Now we can keep people alive in wrecks that are up to 45, 50.
So if you drive a super old car,
Because what?
if you drive a super old car,
If you drive a who car?
old car.
An old car.
Well, now you can put a seatbelt.
Every year we get more safety features in our car, which means our cars are more expensive. And so poor people still have to buy older model cars because that's all they can afford is an old used car. So.
So we're like classic.
Right. Classic cars, you're gonna die if you get in a bad wreck. Okay. Anyway. Okay. Does everybody understand that whole impulse concept now better?
Yes.
And you're all gonna wear your
Inertial restriction.
all the time, every single time. You can't say, okay, I'm gonna freeze time and let me make it click now that I know I'm gonna get in a wreck. You don't know what's gonna happen. And I guarantee it's gonna happen this time in your lifetime more likely than later in your life. Most of the wrecks that happen to you guys at your age. Because you guys all drive like you know what you're doing, and you don't. Which is why there's 3 accidents outside of school every single day. Yeah. Okay. Anyway, how do objects collide? They go boom. Okay. No, there's 3 different ways that we talk about collisions. One is elastically, and in an elastic collision, you bounce. What's an example of an elastic collision?
Bumper cars.
Bumper cars. What's another example of an elastic collision? Who? When Bob goes bowling and he hits a bowling pin, they bounce off each other, right? That would be elastic. When a tennis racket hits a tennis ball. When a baseball hits a baseball bat. Those are all elastic collisions. Now, we have inelastic collisions, and an inelastic collision is when they stick together. So if I throw a spear into you, that would be an inelastic collision. But it doesn't have to be that dramatic either. If I throw a football to you and you catch it, the football and you used to be separate objects, now you're together, one object. If you tackle properly, that is also an inelastic collision. However, I see a lot of people trying to tackle elastically because they think, hey, I'm going to get on TV because I had this nice big hit. So they try for this epic hit and they just bounce off the guy, and the guy's got really good balance and he just goes over a foot and stays on his feet and keeps running. And then a different highlight shows up and you look stupid. So if you're tackling, wrap up. Make it inelastic. Stick together. Okay. The third type is explosions, and explosions are kind of like backwards crashes, where you weren't moving beforehand and then afterwards you're both moving. So this could be something that's literally an explosion, like a gun firing. When a gun fires, then the momentum of the bullet forward and the momentum of the gun backwards are equal. But it doesn't have to involve an actual explosion. If I'm holding on to Bob and I throw him forward, what's going to happen to my body? It goes backwards. There's no way that I'm going to stand and throw Bob hard and me standing here. I'm going to have to step backwards because that momentum is going to shift me. And so when you shove on that something shoves back on you. And actually, Newton, when he explained his third English and second English, explained it in terms of momentum. So he actually used those terms. But yeah, so that's what's going to happen in an explosion. But anyway, the underlying concept of all of these is the same. We're going to have different formulas for each one, but the underlying concept is the momentum before the collision equals the momentum after the collision. And as long as we understand the momentum before equals the momentum after, then the formulas and how they came to be make total sense. So, yeah. Since we have two objects colliding on each other, they have to push on each other with the same force for the same time, so the impulse on both objects has to be the same. So, we know an impulse causes a change in momentum. If they have the same impulse, they're going to have the same size charge. So if I punch you in the face, your face punches my hand, how hard?
Same.
Just as hard, but in the
Opposite direction.
Now, is it possible for my hand to hit your face for a different time than your face hits my hand?
No.
No. So the force is the same, the time is the same, the impulse is the same. Which means your face now has momentum that it received from my hand, but my hand lost momentum because it punched your face. So my hand slows down, lost momentum, your face sped up, gained momentum. So the amount of momentum that your face gained was equal to what my hand lost. When Bob hits a bowling pin, does Bob look like he lost much momentum? No, because his mass is big. So it's not the velocity that's conserved, it's the momentum that's conserved. So Bob slows down a tiny bit, the pin speeds up a lot because the pin is much lighter than Bob was. So that's going to work kind of like that. So anyway, forces have opposite directions, so it seems like one is losing momentum, the other one seems to be gaining the momentum, but again, the momentum is shifting. So that little mark, the apostrophe stands for its prime, it stands for after the collision. So momentum before equals momentum after. So that means if I have two objects that are both moving, if they add up to 100 Newton seconds of momentum before they collide, then after they collide, there's still going to be 100 Newton seconds. So you might have 50 and 50 before the collision, and you might have 80 and 20 after the collision, but the total is still 100 both times. So the total before still equals the total after. Groovy. How do we find the explosion formula? Well, the explosion formula is super simple because before we made it go boom, or before we threw it, or before we whatevered it, there was no momentum, so the momentum afterwards must still add up to 0. So it's still going to be 0. So all the pieces considering direction are going to cancel each other out. So if there's only two pieces like in a gun, we say there's no momentum before I pulled the trigger, afterwards those two have to add up to what they were before, so they must be equal but opposite to each other. And again, since P equals mv, we're going to say m1 v1 equals negative m2 v2. So this is saying, hey, when I shoot that gun, I have a little tiny bullet. So the little tiny bullet has a little m and an enormous V, and the gun is much bigger, so it has a big M and a small v. So that's what happens. So the gun doesn't fly as fast as the bullet goes, which is a good thing. Otherwise, you'd never shoot a gun more than once. Yeah. But that tells you if you have a large caliber rifle and you're shooting a bigger bullet, so if this M is bigger and this V is still big, then what's that tell you about the size gun you want? Yeah, you want a bigger gun. So a larger caliber rifle, you want a larger mass gun so it doesn't hurt so much. Yeah. So if you're shooting little tiny bullets, then the gun can be a lighter gun. Any questions on explosions? Super simple. This would be the same thing if I threw Bob, Bob would throw me. Same velocity, or same momentum on both sides, but who would have a bigger velocity? If I threw Bob, who's going to have a bigger velocity afterwards, me and Bob? Bob would have a bigger velocity because he has a smaller mass.
Yes.
So yes. Okay, if we go to elastic formulas. Elastically, we're bouncing, which means before and after the collision there are two objects. So again, the momentum before equals the momentum afterwards. So before we have the tennis racket and the tennis ball, and afterwards we still have the tennis racket and the tennis ball. And again, since P equals MV, we have M1V1 plus M2V2 equals M1V1 prime and M2V2 prime. Only the V changes, the mass doesn't change. The tennis ball stayed the same mass, it just changed its velocity. So only the velocity portion has the little prime mark because it's the only part that changes. The only problem with this formula is I need to know what one of the velocities is afterwards before it's useful to me. Which sometimes we know and sometimes we don't know. But that logically again should tell me that this works nicely. Now, again, this could be 20 beforehand, and this is 80 beforehand, and then afterwards this is 40, and this one would have to be 60. So it's not saying that this stays the same as that, it's saying the total over here equals the total over here. It could be shifted around all at once too. The total before was 100, the total afterwards will still be 100. It just gets shifted around. Okay, our last type was, okay, I'm sorry, this is still with the elastic. Elastic, like I said, it's not as useful as a formula because I have to know what one of the final velocities is before it becomes useful. So if we combine the conservation of energy and the conservation of momentum concepts and throw those together, we end up with these beautiful equations, which you'll need to write down. So I'll give you a moment to write those down. This is elastic, and these are really nice because this allows us to predict ahead of time what's going to happen in a collision. We know what both of them are afterwards. The reason you have two formulas is the top formula will be the first object afterwards, and the bottom formula will be the second object afterwards. Another good thing about this formula is you will never algebra it. So it's really not that hard of a formula. It looks a little long, but it's not that bad. Yes and no. I mean, yes, you can, but I'm going to explain something in a minute that'll make more sense as to why we tend to draw it this way. Okay. Now, if we come along, if say we're having a bowling ball hit a bowling pin, then M1 is much bigger than M2, right? So if M1 is much bigger than M2, then what's going to happen up here? I'm still going to,
Close to M1.
yeah, it's still going to be close to M1. Now, if I subtract it on top and add on the bottom, but M2 is small compared to M1, then I didn't get a whole lot smaller on top and I didn't get a whole lot bigger on the bottom, which means I didn't get a whole lot slower overall. So V1 and V1 prime, it's just going to slow down a little. Does this make sense? Okay, now, if we come over here, V2 would be the velocity of M2. So how fast is the pin going when the bowling ball comes along at it?
Pretty fast.
How fast is the pin going when the ball comes at it?
Oh, it comes out at 0 times.
It's 0. The pin just sits there. It's not rolling toward the ball. It just sits there and waits to get hit. So this is the velocity. Hey. So if the pin is not moving, then
0.
that's just going to go on. And if the pin's not moving on the bottom, this just goes away. Does this make sense?
Yeah.
So yes, if the second one is not moving initially, then the right side just drops off completely. So this is saying, okay, the bowling ball is going to slow down a little bit. Slows a bit. But what's going to happen to the little one? Well, if we look at the little one, okay, here we say we have 2 M1 V1. And then again here I'm adding almost nothing. So here I have twice on the top and just 1 on the bottom. Tiny bit bigger than 1 on the bottom. So this means that V2, the pin, is going to come out 2 times as fast as the bowling ball came in. Slightly less than that, but yeah, approximately that. So this just tells me, hey, this should just slow down a little bit and this should go out really fast. And if you've ever been bowling and you hit that last spare pin, you'll notice that that's indeed what happens is the ball slows down just a tiny bit and the pin goes real fast off of that thing. And same thing happens when you're, say, playing golf. If you're playing golf, then you have a golf club, but that golf club isn't just the weight of the club, it's also the weight of you because your whole body is swinging through that thing. And so you've got, well, that's assuming you actually make contact, yes. But okay, so your body is swinging toward a little tiny ball like this, and so what happens is when you hit it properly, you don't feel like you hit anything, which means you barely slow down at all. But how fast does the ball come out? Pretty fast. It comes out about twice as fast as the club hit it. So if you have a swing speed of 90 miles an hour, then this ball's going to come out at probably like 170, but yeah, it's going to come out almost twice as fast. So what does that tell you about standing in front of somebody who's hitting a golf ball?
It's a good idea.
It's a great idea. If you're suicidal. So, okay, now what happens if you have a little thing that's hitting a big thing?
Oh.
That's not moving. Okay, we'll still drop this part off and we'll still say that's not there. So the little thing comes along and hits a big thing. So if M1 is smaller than M2, what's going to happen? That's going to give me a negative answer, which means your small thing will hit and then bounce backward. But then the big thing here, again, if M1 is small, then 2 times M1 is smaller than M1 plus M2, because M2 was the bigger one, right? So the bottom got quite a bit bigger. The top one didn't get as much bigger as the bottom one did, which means this is going to be slow. Which means if you have a little thing coming into a big thing, the little thing's going to bounce backwards, and the big thing's going to go and go slowly forward. Now, what happens if we have 2 objects that are equal in mass?
That's explosion.
One is just sitting there, the other one comes along and hits it. They're equal in mass. If M1 and M2 are the same mass, then M1 minus M2 is going to give you 0, which means this is going to be 0. So this is going to...
Wow.
Okay, so that one's going... Wow. Okay, shut up. Anyway, here if M1 and M2 are the same size, then M1 plus M2 and 2M1 are the same size. So this and this are going to cancel out, which means V1 equals. So that means it's going to come out the same speed it goes in. How many of you have ever played pool before? If you played pool before and you hit a nice straight shot, what happens is the cue ball comes in and it hits it and it stops and the other ball moves forward at the same speed that the cue ball came in at. Right? Have you seen this before?
Yes.
Okay, so these formulas work. This is what we're telling you. Now, what if they're both moving?
Oh,
Oh,
no,
sorry.
don't give us tricky questions.
I hate when I do that. This is good. Just ignore this for a second.
Ruin it for Sina.
Yeah. It's okay, keep it. Hi T-Bass, we love you. Okay, now if they're both moving ahead of time, again the thing we gotta worry about is direction. If they're both going the same direction and V1 was going faster than V2 and it hits it from behind, then this one is positive and this one is positive, right?
Yeah.
But if they're hitting head on, if they're going opposite directions, if they're running toward each other, then we call the first one positive, we're going to call the second one negative. And so if you forget to do this, then everything's going to mess up. So again, you got to watch your direction. As long as you're watching your direction, you'll be in great shape. Okay. Our last formula then is going to deal with inelastic. And inelastic, again, we have two objects that start the collision. Only one comes out because they are now stuck together. So again, P equals P prime. But beforehand, we have two objects. Afterwards, we have one object. Since P equals MV, then we start off with M1 V1 plus M2 V2. And what do we put for the M over here?
M1 plus M2.
Yeah, they're stuck together. So they're stuck together. We show that by adding the two masses together. So if I'm throwing Bob toward you and you catch him, then your mass and Bob's mass are now combined, and the velocity is going to be somewhere in between. And again, you have to watch direction. If you're both going the same direction, then V1 and V2 are both positive. If you're going in opposite directions, then V1 is positive and V2 is negative. And whatever this comes out to will show you which direction it's going afterwards. So, super simple, right?
Yeah. You say that now and then we get the homework. I know. And then we cry. No, the test.
Okay.
Test.
So your homework is to do problems A for today. Hooray! Hooray!